Hello friends, welcome back. In this video, I am going to discuss March 1976 research paper by Elliot Bell and Leonard La Padula, famously Bell La Padula pair. And this research paper is a very important research paper. It was published in 1976 and it tried to give a unified idea of the previous three research paper, which talks about mathematical foundation and some sort of abstract idea of a secure computing system, right? The name of this research paper is Secure Computer System, Unified Exposition and Multics Interpretation. So Multics is an acronym which is for Multiplexed Information and Computing Services, and it began at MIT as a research project in 1965. It was in use till year 2000. So Multics is an influential early time sharing operating system based on the concept of single level memory. It was basically mainframe time sharing operating system. So that's all about Multics. So this research paper has got 4 sections. Section 1 is obviously the introduction, and section 2 is a narrative description of the security model. By narrative description, it's meant that the system is explained in a way which is understood without going into the details of mathematics, right? So that's the narrative detail. And section 3 is more mathematical, and section 4 is something which is related more with the security kernel design and of higher design and technical details. So we are not going to discuss section 3 and 4 in this video, for the obvious reason that making a video of the mathematics behind a system is difficult, right? It need a whiteboard session, basically a 101 class in which we can explain those things. This is one reason. Second reason, I myself am not that capable in explaining those mathematics in a very general terms to all the people, and this is not required in CISSP exams as well. So section 2 is something which we will focus, which is the narrative description of the Bell La Padula model, and this will give you some background and it will give you some information which will be helpful in your CISSP exam. So stay with me and let's dig down section 2 of this research paper. So the description of the security model, as Bell La Padula explained in this research paper, is more like a general description as we have in our experience. If we look back in our school days, we look into a human cell as a typical human cell that do not necessarily exist in that shape and size in the part of the body, because every cell is different, but we make a typical cell to explain the components of it. So in the same way, Bell La Padula talks about a descriptive model of a secure system, and this model is going to have 3 different facets of its existence. So the security model, as explained by Bell La Padula, this model can be viewed as having 3 major facets: a descriptive capability, which is the element of the security model. So any security model is going to have certain elements, and those elements will make that secure system. So that's one part. So first is the descriptive capability, which will explain the elements of the security or the elements of the secure system. The second component of the security model is the limiting theorem, which will explain the general mechanism of the security system, right? So first is elements, second is limiting theorem. Limiting theorem, you can understand general mechanism, how the secure system is functioning for its subjects and objects, like that, how the relationship is maintained for different type of operations in the system. And the third facet of the secure system is general rules. Those rules will be specific to certain solutions, right? So you can have a visualization of a secure model with elements, limiting capabilities, and or limiting theorems and rules. So these 3 things you should have in your mind. So when we talk of description of the model, we are basically talking about elements, limiting theorems and rules. Elements are the descriptive capability of the model, as in, like, if I am talking about the model of a car, then we will be talking about the car has got wheels and a body and a steering wheel, and then we have got ignition, we have got transmission. So those are the elements of the model. Similarly, for a secure models, we will be having different security elements which will define its descriptive capability. Then we will be having the general mechanism, how the security model is treating its subjects, objects, and what are the different access attributes related with the interaction between subject and object, that is defined by limiting theorem. It is called general mechanism. Then we have rules for a specific solution in a specific condition, how subjects will be trying to access an object. Will it always follow a defined set of rule, or if there is an exception, how it will treat. So when we talk of elements, what we understand by this term in the security model is element is anything, any component of a secure model or a computer system that are relevant to the treatment of classified information stored in the computer system. So there is some data information in the computer system, and all those components which are gonna have an effect on that information, those components are called elements. So when we talk of descriptive capability of the model, which is elements, what we are trying to address here? We are trying to address here a basic question. The essential problem for this security system is to control access of active entities to a set of passive entities based on some security policies, right? So these active entities are called subjects, denoted with S collectively, or an individual subject is denoted using SI. Similarly, for objects, it is collectively denoted with O, and OJ is the individual object, right? Now the next thing about this descriptive capability we have to understand is that the model, the security model, will constrain the entities, which is subject or object, role based on security policy. So whatever security policy we have for the secure computing system, that will rule, that will actually constrain how this relationship can exist. Now as we see here, like, we have got different subjects, S1, S2, S3, S4, O1, O1, O2, O3, O4 are the objects. Now this access in the model can assume different modes, right? Now these different modes are called access attributes, right? So if we have to define what are the access attributes, we can say that the access which is from subject to object in a secure model can assume different modes. These modes of access in the models are called access attributes. Now further, to visualize the access attributes, we have a subject and then we have an object. Now the two effects that an access can have on an object is either extraction of the information, which is the observing the object, or insertion, which is altering the object, right? So these are the two effects which can happen as part of the interaction between a subject and an object. Now there are thus four general type of access imaginable. The first one is no observation, no alteration, which is denoted with execute. Then we have observation but no alteration, and then we have alteration but no observation, and then we have both observation and alteration. Now these four types are basically our discussion in this research paper, which is denoted using E, R, A and W. Now no observation and no alteration is denoted using E, or we can have an E bar below E, which is called E access, it means execute. R access is called read, A access is called append, and W is write. The thing which we should note here is that execute, as we understand in our day-to-day life, that execute means we are just double clicking on something and a program runs. Here execute means no observation, no alteration. It's just a denotation of the system is being ready to accept a subject, right? The system is ready, it means, like, you can think of a computer is on, a subject can interact, so that is in an execute mode. And in this mode there is no observation, there is no alteration. In observation but no alteration, which is called read access, it's just a read only access. Then you have got append access, like a subject is pushing some data into object, but it's not reading anything, right? So that's append access of alteration but no observation. Then you have got both observation and alteration, which is called W access, write access. Now we have understood subject, object and access attributes, 4 access attribute E, R, A and W. Now let's define system state formally. Like, what is a system state? Now system state, the state will be expressed as a set of 4 values, and these set of 4 values will mathematically define system state. Each value referred to as a component of the system. Now as you see in my drawing, current access system state is referred as a set of 4 different values. The first value is called current access set, which is denoted using B, and this current access set is nothing but subject, object and access attribute. What are the different subjects, what are the different objects, and what are the access attributes related with that those subjects and objects. Now second system state attribute is hierarchy function H, which is the object structure, and third value is access permission, which is denoted using M, which is basically an access matrix, and the fourth one is level function, which is denoted using F. I think I have written L in my drawing, which is wrong. We can denote using level function with L, but in the research paper it is denoted using F. So in later on I will always use F for level function. So level function is a set of classification, a set of categories. Classification, as we all know, in domain 2 data classification, we have got different classification levels of data which we have in our organization: top secret, secret, confidential, private, those kind of thing. And set of categories are like different, this data is categorized into different category, like you can think of HR, finance, corporate, production, those kind of classification. Now if you look into hierarchy is basically the object structure we denote using H. If you see in the drawing, we have got different files which may have parent child relationship, and that is basically used in that value, which is hierarchy value. Now let's look into the access permission, which is access matrix M. Now access matrix M is basically a table, which this table explains what are the subjects and what are the objects, and what kind of access attribute is related with some subject and object, right? So if you have a S subject Si and object Oj, then you have an intersection point where you will be having Mij, which is M, as we are denoting access matrix with M, and since it is related with subject S and object O, its cumulative value Ij will be denoted using Mij, and this will be denoting some type of access attribute: read, write, append, or execute. We should also know that the unnecessary condition for a subject's possession of an object is that the subject security level must dominate the security level of the object. This is just a common sense that the subject who is going to access some document or file or an information should have a higher security level than object, right? We will briefly look into security level now. Security level is basically a set of classification, a set of categories. Classification could be unclassified, confidential, secret, top secret, those kind of thing. And category could be, if we look into the military world, it will be like nuclear, NATO, crypto, and those kind of category. In our corporate world, we may have finance, production, HR, and general corporate users, those kind of category can exist. So typically if we have a class 1 category set 1 and it dominates class 2 and category set 2, this domination can happen if and only if class 1 is greater than or equal to class 2, which is the classification level, and category set 1 includes category set 2 as a subject, right? So if these two criteria are met, it means that we have a dominance relationship. Now this drawing which I am going to explain here is denoting some of the term. which we use in secure computer design. One is maximum security level. Maximum security level is denoted using level SI, right? So because we are talking about security level and we are denoting security level with letter F, so we will say FS, and SI is the individual security level, is called the maximum security level here. So FSSI or level SI, if this term is represented, it means it is showing the maximum security level of a subject. Now the other term is FCSI, which is the current security level of the subject. Now for a communication to be secure or for a transaction to be secure, the current security level of the subject should always be lower than the maximum security level of the subject. If this is not true, it means that there is some kind of security elevation which has happened, right? It's like a normal read-only user is given a super user account. Similarly, we have for object, the level OJ is denoted as the security level of the object, and then you have FCOJ, which will be the current security level of the object. So in my drawing, I have written FOOJ or level OJ as maximum security level, which is not correct. It should be only security level, right? Because for object there is just a security level OJ, but for subject it can vary. It can have a current security level and maximum security level. So for security, it is required that the level SI, which is the maximum security level, should dominate current level SI, which I already explained. A triple of security level assignment function, which is FS, FO and FC. Now what is FS? FS is basically the security level of the subject, and FO is the security level of the object, and FC is the current security level of the subject. Now this triple of security level assignment function is called the level function, which we denote using F. A state of the model is a fourth tuple of the form. Now if we combine all the discussion which we have about current access set, access permission matrix, level function hierarchy, this BMFH, B is current access set, M is the access permission matrix, F is the level function, and H is the object hierarchy. These four values will explain the current state of the system. Now if any of these four value changes, it means the state of the system has changed. So we have a system, and system is denoted using S, and we have got different inputs coming into the system. Let's say those inputs are R, and Rk is some individual input. Then the system will do some analysis or some processing of the input, and it will make some decision DM. The state of the system, as I already explained, it is BMFH. The system is all sequence of request, decision and state. It will get some request, it will make some decision, and it will reach it to some state with some initial state Z0, which satisfies the relationship W on successive state, right? So this is how a finite state machine concept is being used in a secure computer system. Now the takeaway of this whole discussion of this research paper section 2 is that a system state is defined. A system state is defined using four values, B, M, F and H. The first value is current access set B, and this current access set defines what is subject, what is object, and what are the access attributes. And access attributes can have four different values, or they can be of four types, which is execute, read, append and write. Okay, so this is one value of the system state. The second value of the system state is the hierarchy function, which is basically the relationship between different data sets which we have in our information system. And the third value is the access matrix. Basically this is you can think of an Excel sheet with subject and object as columns and rows, and we define a value, access matrix value for a specific subject and a specific object, and we see that what access attribute exists for that subject object relationship. And then we have level function. Level function is basically a definition of category and assigned classification. So we classify data and then we categorize them according to our need in the organization. So the classification can be like top secret, secret, private and general public use, and that can exist in our organization hierarchy in terms of some category, right? So category set 1 can have only top secret data, category set 2 can have only secret data, category set 3 can have some top secret and some secret data. So we can design as our need is. So these 4 values define system state, and our system works on some rules, and some decision is made for every input and output, and that's where we think of a secure computer system in terms of this system state. And once the system state changes, it goes into another system, another state, which is a different state, and we try to maintain those states within the parameters which we define. That's all about this research paper, and we will quickly see what is the outcome of this Bell La Padula model, which we should keep in our mind for CISSP exams. Now the outcome of this model I will explain using this diagram which I have created when I was preparing for my CISSP exam. If you look into this diagram, I have this screenshot of one of the movie I watched. It's called Valkyrie. I don't know if you have watched this movie, but it's about a military coup which was done against Hitler, and this picture is iconic in terms of the topic which we are studying here, because it talks about confidentiality. So whenever we talk of Bell La Padula model, we should always think and always have this in mind, that this model is talking about confidentiality of the information, and the different properties which we will be talking here is simple security property, which is called no read up. So if a subject has got a lower classification level than the object, then that subject is not allowed to read the data. So no read up. The subject can read at its own level, and subject can read down the level. And then we have got a star property which says that no write down. So this, if we have no write down, it means that the subject can write data to a higher level and data to on his own level, but the subject cannot write data to a lower level. This is based on 3 separate state machine properties. One I already explained, which is simplest security property, no read up. The second is a star property, which is no write down, and then we have discretionary security property, which is use access matrix to enforce discretionary access control. So these 3 things we should always keep in mind from exams perspective for Bell La Padula model. And we should also keep in mind that this model do not support file sharing and networking, and do not address covert channels. So this is how Bell La Padula model is. I hope you understand this topic. The key takeaway for the exam is that this is based on lattice model. It's based on 3 state machine property, which is simple security property, star property and discretionary security property. And that's all. Hope you enjoyed the video, and best of luck for your CISSP exam. Let's meet in another video where I will be discussing BIBA model and Clark-Wilson model.